So these are our electricity notes. This is a picture of Ben Franklin. He's the person who's most famous or most well known for this topic of electricity. So he was curious about lightning. He was wondering if lightning and electricity were the same thing. Did lightning have electricity or an electric charge to it? So what lightning is it's when there's a buildup of electric charge in the sky, and once that gets so big, it jolts down to the earth in the form of lightning. And electricity uh, seemed very similar to him. So what he did, his famous flying kite experiment, which was really dangerous at the time, his goal was to collect that lightning and have it transfer down to this metal key. And if he was to feel that electric shock, he can kind of conclude that lightning and electricity were very similar. And he did do that. He actually invented the lightning rod. So if you had a metal pole on top of a house, that lightning would strike the pole and therefore not the house, protecting it from that electric charge. I'm sure you guys have experienced an electric shock before. When you touch something and you get shocked, or maybe when some people have tried it when you're in socks and you create friction on a carpet, you have an electric charge to you. We're going to figure out what that's actually all about. So an electric charge is a property of matter. The unit for this is called a coulomb, and a charge can be positive, negative, or neutral. This is also pretty well known. You guys should be familiar with this. Like charges are going to repel one another, where opposite charges are going to move closer to one another. They're going to attract. So how does this actually happen here? So we think back to our atom when last semester in chemistry. We have protons, we have neutrons, we have electrons, right? The protons and neutrons are staying put in that nucleus. Therefore, the electrons are the only ones that are able to move. Remember what charge an electron is? Electrons are negative, okay? So electrons are transferred from one material to another. And since electrons are negative, they're always going to move over to the positive object. Some more terms that we need to be familiar with are conductors and insulators. We talked about these words when we were on the heat and thermal energy units. They mean the similar things here. So conductors are things like wire and metal that allow the electric charge to move past them. So these conductors are allowing those electrons to travel through the object and reach the positive object. Or insulators, like cardboard, glass, or plastic, they're going to prevent the charge from moving. So they're not going to let those electrons travel through. Think about any electronic objects you have, whether a toaster, a lamp, or your phone charger. Those wires are covered with the rubber outing, right? Why is that? We need that insulator around those wires, or every time we touch that wire, it's going to conduct, it's going to transfer that electric charge to our hand, which would not be a good time. So we always have those rubber coverings over these wires for our safety. So these are our ways that objects can be charged through contact or through friction. So think about, I'm sure many of you guys have tried maybe this balloon trick where you have a balloon, you rub it against your hair, and your hair is sticking to the balloon, right? So what's happening is the electrons from the balloon are transferring over to your hair, okay? So now for the balloon would be more positive, right? It's losing electrons, so the balloon is positive. Your hair is gaining electrons, so your hair is now negative. Therefore, opposite charges attract, so your hair sticks to the balloon. So there's some important terms that we need to know and be familiar with electric flow. One of them is voltage. So this is a difference in charge between 2 points. Easy unit for this one, voltage is measured in volts. So if I have two objects that have different charges. One is positive, one is negative by this amount. The difference in charge, that's what we call voltage. So if I have something that has a high voltage, that means there's a large difference in charge. And if I have a small voltage, they're pretty close to one another. Remember, the more similar the charge is, they're not going to want to be close to each other, right? Similar charges repel, or different charges are attracted. The next important term is called current. Like a current in the water, it's a motion, right? It's a rate at which the charges are moving through the wire. The unit for this one is going to be amps. So if I have a high current, that means that those electrons are transferring really fast. If I have a low current, those electrons aren't traveling as fast, they're traveling pretty slowly. So electric charge, we need that opposite charge. We need a positive, we need a negative in order for that charge to keep moving. A standard outlet is designed for about 120 volts, so a difference of charge of about 120. Some things need less electric energy, right? A simple, let's say, toaster uses less energy or electricity than a refrigerator, right? So how do we make up for that if all of our outlets are basically the same? Well, if something needs less electric energy, we use these things called resistors. Resistance is slowing the movement of charge. If you're resisting something, you don't really want it to happen, right? So resistors are controlling the amount of current that goes through. This is a different unit. This is measured in ohms. The symbol that we use for this, which might come up, is this little omega symbol. Okay, so these three terms here, voltage, current, and resistance, are important to differentiate. Probably a question I'll ask you is basic definitions of them and simply matching to the right one. All right, let's talk about this thing called Ohm's law. We have a little bit of math here. So these three important terms about electricity can be related into an equation. The voltage is equal to the current times resistance. So if something or somebody's trying to figure out an electric path for an object to work, if you know 2 out of the 3, you can use this equation to calculate, how much resistance would this cord need, or how fast are these electrons traveling here? What's my current, So using our triangle method, we've done this plenty of times before. I can use the variables and come up with 3 separate equations, okay? So quickly going through these, an alarm clock draws 0.6 amps of current when connected to a 125 volt circuit. Calculate its resistance. So resistance, if I look at this triangle up here, I'll cover the R, I'm left with V over I. So voltage over current. What's my voltage? You should look at this problem and pull out 125. My current is 0.6. So if I simply divide those numbers, I'll get an answer of 208.3 ohms. Next one, a circuit contains a 1.3 volt battery and a bulb with a resistance of 3.4 ohms. Calculate the current. So I want current, I'm going to cover up the I. I'm left with voltage divided by resistance. So if I'm looking at this problem, what's my voltage? My voltage is 1.3. My resistance is 3.4. So if I divide those two numbers, I would get an answer of 0.382 amps. And how much voltage would be necessary to generate 14 amps of current in a circuit that has 5 ohms of resistance? So I'm asking for a voltage here that is going to be current times resistance. So somehow I went back, excuse me, let me get to where I'm going. Current times resistance. My current in this is going to be 14. My resistance is going to be 5. If I multiply those, I get an answer of 70 volts. So this is in our notes. We're going to be looking at this website to answer those. So I have this website pulled up, and we're going to kind of look at the relationship between these variables while you guys answer these questions with me. So I have voltage is equal to the current times resistance. And if we mess with these variables, we're going to see how it affects the other things. So our first question is, what happens to the value of the current when the value of resistance increases? So if I take this resistance, remember resistance is slowing down the current. So look at my current right over here. I'm going to increase the amount of resistors. So what's happening here? I'm increasing my resistance, therefore my current is getting smaller, right? So what happens when I increase my resistance? Well, my current is going down. What happens to the value of the current when the value of the voltage increases? So I'm going to reset it. This time I'm going to increase my voltage. Keep an eye on my current, okay? So I'm increasing my voltage, the difference of charge. So my current is also going up. So what happens to the current if my voltage increases? My voltage is going up. And what's the relationship between current and resistance? So if I change this, notice my resistance. If I move my resistance down, my current is going up. If I move my resistance up, my current is going down. So they're essentially opposite. So we're going to have to split this note section up into 2 videos. So the last thing I want to talk about in this segment of this video before my time is out, we're going to talk about how batteries are working. So battery has stored electric potential energy. So I have this potential energy inside of a battery. When the device is on, energy from the battery is then transferred to the device, causing it to turn on. So when this battery is inside of a device and you turn it on, it's allowing the path of electrons to travel through, allowing it to work. So it has this already set amount of energy. So why do batteries die? Why don't they last forever? It's simply the amount of energy that it had to begin with is running out, and it eventually is completely empty. Therefore, that's why you have to replace your batteries. So I have one more topic of circuits we're going to talk about, but that's going to have to be in the next video. So make sure you click that to finish up our notes.